starts.
Good afternoon, and thank you very much for inviting us here to present our proposal to you today. We are Aquadizer Solutions, and we have been tasked to come up with a chemical oxidation process to remove N-methylpyrrolidone, or NMP, from the water reclamation project at the IBM plant up the Diagonal Highway in North Boulder. My name is Eli Townsend, and I will be one of the Advanced Oxidation Procedures, or AOP, experts, and I will also be this project's manager.
I'm Alex Copeland, and I'm also an AOP expert and a drafting technician.
My name is Matthew Zapataki. I'm in charge of scheduling and budgeting, and I'm one of the regulation experts.
I'm Noah Baker. I'm in charge of quality assurance and one of the drafting technicians.
I'm Robert Redfield, and I'm also an AOP expert and a regulations expert. I'd like to take this time to thank Professor Linden for being here as our faculty advisor and representatives from IBM. We appreciate having you. Okay, so just a little bit about where we're going to go today. We're going to present the problem that we're tasked with, and then we're going to present an outline of dates that we're going to try to meet in the future, and also quickly run through some of the oxidation procedures that we've done research on. Once again, this isn't a very well-studied chemical, so pilot studies would have to be done to characterize any system. I just kind of want to throw that out there before all this is tentative. So. Okay, a little bit about NMP. These are some of the chemical properties. Two of the chemical properties that stood out to us, the fact that it has a really high boiling point and that it's very miscible in water. So this makes physical removal mechanisms very difficult. So oxidation, either through biological means, as the previous group demonstrated, or through chemical means, are the only economically feasible methods of removing this from the wastewater stream. These are some of the industries that it's used in. It's primarily used for the recovery of hydrocarbons, but Lexmark uses it to strip toner cartridges, as we'll see. Yeah, so Lexmark, which is also located in Diagonal Highway, uses NMP to strip toner cartridges, and they're under contract with IBM, so IBM treats the wastewater after it's sent there. Originally, the stream was diluted prior to 2008, I believe, and for a number of reasons, Lexmark decided to stop using deionized water. They stopped mixing the streams, so it's no longer diluted, and we see a concentration influence IBM at 300 milligrams per liter. As you can see from these other flow parameters, it's a pretty low scale operation. To put this 24,000 gallons per day in context, an industrial wastewater treatment process treats millions of gallons per day, so this is small scale. After the biological treatment that IBM currently uses, we're seeing that there's a 30% removal. Okay, so again, these are the dates that we're looking at. We're going to provide an alternatives assessment to IBM on the 14th of March. This is going to narrow down a lot of today we're going to throw 8 possibilities at you, and we're going to narrow these down based on cost and efficiency. And then on the 30th of April, we're going to present a final design, which is going to we're going to narrow it down to one method, and we're going to have all the parameters and cost-benefit analysis is done.
So the current removal system that IBM has in place has an influent concentration of NMP of 300 milligrams per liter, or 300 parts per million. This is due to the fact that they can't dilute their waste stream at Lexmark anymore. And the current main process of removal in this system are these 2 rotating biocontactors. This is a front view, so this is like the size of the disc, and it exists both below and above water, and this is constantly rotating to allow for anaerobic and aerobic digestion to occur. So it promotes multiple degradation pathways microbially. And as you can see here, there are many plates in parallel in one of these RBCs, and it's in the spacing. There's very tiny spacing in between the plates, and that's where the communities of the microbes are growing. As the previous group stated, the current RBCs, one of them has an efficiency of 30%. IBM believes that if they add oxygen to this water down here through a diffuser, they can increase the aerobic degradation in the anaerobic phase to promote more degradation of the NMP. Potentially, they believe they can get this efficiency up to 35% per RBC. So if they have both of these RBCs online, only one's currently online, that means the efficiency could potentially be up to 70% efficiency of removing NMP in the system. So this is a current schematic of the reclamation system in place at IBM. This is where our influent parameters are given. We know ammonia concentrations as well as other hydrocarbon concentrations at this point. And this is where the 300 milligrams per liter occurs. The water then flows into an equalization basin where solids are settled out. There's then a flash mix coagulation tank which flows to a clarifier to let the flocks, if any flocks are formed, to settle out also. The water then proceeds to the 2 RBCs, of which only one is currently online. They're in parallel, as can be seen here. And then the solids and the water goes to a bioclarifier where the microbes can be settled out. From there, the water proceeds to a chlorination tank where the stream's dosed with liquid hypochlorite. This acts as a biocide throughout the system in order to maintain low to minimal to none biogrowth to prevent scaling in the storage basin and in the cooling towers.
So we were tasked with creating an oxidation process for the removal of NMP. There are 2 basic forms of oxidation. The first is known as conventional oxidation, which is where a reducing agent and a oxidizing agent come into direct contact and an electron transfer occurs. The advantages of these forms of oxidation are that they're well understood and they're widely used throughout the water and wastewater treatment industries. Unfortunately, they typically proceed slowly, and complete mineralization of organics is unlikely under most circumstances. The next type of oxidation is known as advanced oxidation, where a hydroxyl radical is indirectly created. These processes are non-selective, and as a result they proceed quickly and at high efficiencies. Unfortunately, some of them cost more simply due to the mechanisms and chemicals that are used, and some of the processes are not as widely understood as conventional oxidation, so pilot studies could be used to further understand these processes. So I'm going to list the 8 methods of oxidation that we identified. The first is ozone as a function of pH. At higher pHs, ozone functions as an advanced oxidant where a hydroxyl radical is created, and at low pHs it's just a normal conventional oxidant. Permanganate is a conventional oxidant that is added in a bulk powder form to the system. Ozone in UV is an advanced oxidation process where the UV creates the hydroxyl radical from the ozone. Similarly, hydrogen peroxide in UV also creates the hydroxyl radical just through the reaction of UV and hydrogen peroxide. And finally, ozone and hydrogen peroxide is just a mixture of the 2 methods mentioned previously. Fenton's reaction is a catalysis reaction involving ferrous iron, hydrogen peroxide, and UV. Titanium dioxide photocatalysis is also another catalyzed reaction similar to Fenton's reaction, only titanium dioxide is used. And finally, ferrate oxidation is a conventional oxidation method where ferrate salts are used as the oxidant. These 3 advanced oxidation processes all use UV light to create a hydroxyl radical. Between the 3, ozone and UV and hydrogen peroxide, ozone and UV are the most efficient. However, the 3rd option typically requires a lower ozone dose, which is beneficial if one wants to keep bromate from forming in the system. The following design requirements are necessary for each of these options. First, a UV contactor would be required for the system. Hydrogen peroxide must also be well mixed throughout the system. And hydrogen peroxide itself is explosive and is therefore a risk to Homeland Security and regulated by the Department of Homeland Security. Finally, if ozone is to be used, it must be bubbled through the system by way of a diffuser. It must also be produced on-site from liquid oxygen, which can add to its cost. And finally, off-gas treatment may be required for ozone to meet national ambient air quality standards.
So just a quick rundown of what a catalyst is used for. A catalyst is something that allows the reaction to proceed much more quickly, but is not actually consumed in the reaction. We're going to be looking at two potential catalyzers to oxidize NMP. The first is titanium dioxide. This actually is a reaction that takes place on the surface of titanium dioxide, so organics and UV or radicals sorb to the surface and the reaction proceeds much more quickly. In order to use this method, we take a mixture of suspended particles. So we need to add a mixer in order to prevent those particles from settling out. The second reaction is Fenton's reaction. This uses iron in the +2 oxidation state to oxidize hydrogen peroxide in the presence of UV. And this actually allows the hydroxyl radicals to be produced much more quickly, so it acts as a catalyst. It's pH dependent and would need to be initiated at pHs of lower than 2.5, so that's definitely a limiting factor.
So a new oxidation method that has come about within the last 10 years is the use of ferrate salts. And ferrate salts are just higher valent iron oxides, such as iron 6 or iron 5. And the benefit, one thing that's really attractive about these, is that they have a really strong oxidation potential because it involves these two electron transfer steps, and each of the electron transfer steps involves a transfer of 2 electrons. And so the transfer potential there is large, so we can oxidize an abundant amount of chemicals with this process. And as can be seen here, rate constants have been shown to favor aromatic amines over aliphatic amines by 3 orders of magnitude, and that's great for us because we're dealing with an aromatic amine.
As Eli said earlier, this is the part of the treatment train we'll be looking at. Right now, we've preliminarily picked the chlorine tank as an addition point because there's already a tank there and already a line in, so it would be an easy place to add chemicals. Also, depending on the method selected, we could add a UV contactor, mixing tank, or anything after that before it gets pumped to the cooling towers. For quality assessment and control of this project, we looked at 5 areas. Individually, we'll all have different parts that we need to self-edit, and we specified more in-depth individual responsibilities in our team contract. We'll be using CATME for peer review. We'll also probably break up into internal groups, and those groups will self-edit so everyone gets a look at everything in the project. And communication and feedback are very important for us, especially verbal feedback as opposed to just CATME. With our client contacts, we'll be emailing John and Aaron at IBM. IBM also said they might be able to provide sampling. And if you look on this point, these are the 2 points we've picked to define our parameters a little more. We think that if we get a sample on either side of the chlorine contactor, it would be able to give us a better idea of what we're looking at. For our resource quality, we want professional level resources, so we're going to be using the CRAP test. This asks questions about 4 different attributes of sources: currency, reliability, authority, and point of view. And using that, we'll be able to assess our sources. And again, there'll be a lot of government regulations that we'll have to abide by. These are the areas that we'll be regulating. The state of Colorado regulates industrial wastewater use. Ozone's regulated by the EPA, and again, hydrogen peroxide is regulated by Homeland Security, Department of Transportation, and OSHA.
Here we have our team design schedule. It lists our primary objectives as a team, as well as the approximate time frame it will take to complete them. The first 3 objectives are the preliminary research we will be conducting. It involves researching the regulatory limits of NMP. It involves analyzing the water quality data given to us by IBM. And of course, we'll also have to look at each oxidative process we've mentioned. We'll use this research to create a cost estimation, which will then factor into our decision matrix, which will include criteria such as economic, viability, environmental sustainability, and technical feasibility, as well as client desirableness, of course. And then we'll also create a quantitative version of this in the form of a cost-benefit analysis. We'll composite this into a written report and presentation, and that'll be due on March 14th. We've done the same thing with the final design portion as well. We'll be creating drawings and flowcharts for this process, We'll also be truing up our cost-benefit analysis as well as our total cost. Then we'll also compile it all into a written report and presentation due on April 30th. Here's our forecasted personnel budget. These are the general billing rates of each role in our team. We forecasted the hours for each position that we believe it will take to do a high-quality job that is standard of Aquadizer Solutions. We just take the billing rate, multiply it by our forecasted hours, and came up with a forecasted budget for each position on the team. We summed that up and came up with a total forecasted personnel cost of approximately $39,000. We are at an interesting time in chemical oxidation techniques. Conventional oxidation is being rivaled by and generally outperformed by advanced oxidation on a lot of levels. Conventional oxidation that we have suggested for IBM's process include ozone in a low pH environment and permanganate. The advanced oxidative processes we looked at for this project include UV and photocatalyst with compounds such as ozone and hydrogen peroxide, as well as titanium oxide. Then we have also included a third method, which is the use of salts, which involves, in our case, the use of ferrate. We would like to conclude by saying additional data and sampling is required for us to choose the best possible alternative. However, we'd like to thank you all, and especially IBM, for being here today. We look forward to working with you, and we look forward to the challenge. Any questions?
Thank you.
So you said that the concentration of the effluent is 300 milligrams per liter. What is the desired concentration output that you guys want?
Zero.
Zero?
Zero.
Okay.
100% removal is the desired effect. Christina?
Back to your schematic.
That one?
Yeah.
Okay.
Why did you choose to sample where you did?
So the first sampling point is because we know that the RBC is 30% efficient, and we don't know how much oxidation happens between the RBC and the bioclarifier. We're assuming probably very little. And then the second sampling point is because coming out of the cooling towers, we know there's zero, so we want to make sure that we want to see where it's getting oxidized. If it's getting removed in the cooling towers by degrading the wood, then there should be some NMP there. If it's not, then it's all getting oxidized with the chlorine or something.
In addition to that, chlorine's oxidation potential on NMP is not well studied. Very few studies have shown that chlorine can directly oxidize NMP, so we want to use this to assess chlorine's oxidation potential. Kurt.
So you're going to sample for NMP?
We're going to sample for a majority of, or a plethora of things. We're going to sample for TOC, NMP, potentially TN, BOD. There are a lot of parameters that we are requesting in this sampling portion.
Any other questions?
Do any of the methods you're proposing produce like a sludge or any residuals that you need to deal with? Then how would you do that in your, if it did, how would you do that in your schematic there?
So one of the possible additions that we're going to add is a settling tank, and so that would allow for like the manganese and the permanganate process to settle out, or the iron and the fenton or the ferrate reaction to settle out. And then they already have a solids thickening bed on site, so this could get added to that.
So is your intent that they would leave the RBCs in service or remove them?
Yeah, that is our intent right now, to leave the one in the RBC in place.
And the reason for that is because it's already removing NMP, so if we know how much is getting removed from the RBC, then we can add less oxidant, and so keep the cost down for our oxidation system.
It would also increase the capital cost of the project immensely to take out the RBC and install a whole new tank for oxidation. I mean, the cost would be very large to do that.
The current estimate that IBM has given Lexmark to retrofit these RBCs is $100,000 per RBC. So
To refurbish.
Refurbish, yes, sorry.
Into a functional.
Yes, into a more more modern bio contactor.
Right, I mean, because given that they're from the 1970s.
Right, they're really old.
Rely on
Right, and
the one that
NMPs
does not keep working, or it'll have a very.
And NMPs degraded very well in the aerobic phase and not as well in the anaerobic phase. So, yes.
So maybe I just have some inside information because I'm not in the other group. Are you guys not worried about additional scaling in the cooling tower with any of these other oxidizing things you plan on adding?
Well, currently they're adding chlorine to keep the biogrowth down. So as long as we add the settling tank and keep adding the chlorine to keep the biogrowth down, then we should avoid scaling throughout the system.
So removing any like iron or
Right, exactly. Any manganese or iron that was added during the previous processes. Any other questions? Thank you all.